welcome everybody. And so today we will have a new edition of the Breakfast Science. So today in Geneva, in HUG building. So we are happy to host today Martin Zach from Michael Unser CIBM Signal Processing EPFL Section. And Martin did his PhD in Austria, in the University of Graz, and he's working now as a postdoc in Michael team in EPFL since a few months, I think. And the expertise of Martin is inverse problem and reconstruction, and in particular with MRI images. And today he will show us mainly what he did during his PhD in Graz. So thanks for coming, and I let you the floor.
So thank you for this kind introduction. Welcome to the people in the room. Welcome to the audience. I'm very happy that I can be a speaker at this anniversary Breakfast in Science, if you want. It's the 50th edition, as far as I know, and I will be talking about what's written here on the title, this idea of establishing trust in data-driven MRI reconstruction. So what's the deal with this magnetic resonance imaging? Well, I mean, it's a very widely used imaging modality in like clinical practice, of course. It has the benefits of excellent soft tissue contrast without being invasive or using ionizing radiation. However, it suffers from one main drawback, which is that of the long scan times. And derived from this drawback, there are some further drawbacks, such as the low patient throughput, the high maintenance cost, and the per scan cost, especially due to the long scan times, as well as the problem that patients that have limited attention spans cannot maybe lie in the scanner for so long. Now, when I was making these slides, I was thinking, okay, this cannot be the intro slide. I mean, it doesn't really look good. And since I'm talking about this data-driven reconstruction idea, I thought maybe I should ask a data-driven model to prettify this slide. And so I asked ChatGPT. I asked it to generate a sketch, so by the means of an image that outlines the benefits and drawbacks, blah, blah, blah. For the drawbacks, emphasize that there are high maintenance and per scan costs, long scan times, and consequently low patient throughput. And interestingly, this is what it gave me. So, not sure if I can like open this, but it should be fine, I guess, for everyone. It gave me something which is sort of weird, because it has two pillars right here on the left-hand side, benefits, and on the right-hand side, drawbacks. And these benefits and drawbacks are very reasonable. So on the left-hand side, we have the benefit of excellent soft tissue contrast and no ionizing radiation. On the right-hand side, on the lower right-hand side, we have those drawbacks, the long scan times and the low patient throughput, which is very reasonable, and it's challenging for patients with limited attention span. But then for some reason, it gave me a second benefit column here on the upper right, where it says that high maintenance and per scan costs is somehow a benefit. So I'm not sure how it came up with this exactly, but I thought it was fitting that, this... I thought it was fitting that this data-driven model, gave me something which is, in my opinion, not quite reasonable, as I'm not an MRI vendor, okay? Okay, so let's continue now with my talk. How can we make it such that, the output of this model, we can somehow trust this, especially in like high stakes applications such as medical imaging? Now, I will quickly talk about the physics of MRI, and the amount of detail I will go into in terms of the physics is basically summarized here on this slide. So on the left-hand side, we have what I will be referring to as maybe the signal, the reference image, or the anatomy, or something like this. And on the right-hand side, we have the data that is acquired by the MRI machine. And the relationship between the image and the data is the MRI scanner if you want. And I will be summarizing the MRI scanner by the Fourier transform. Now, here on the right-hand side, what they call the K-space, there's a lot of pixels basically, and each one of those pixels, more or less, requires time to acquire, right? And to minimize now the scan time and basically mitigate the drawbacks of MRI or of the MRI method, a naive approach would be just to acquire less data. However, if we do this, and we do what we did previously to this data, so we just apply the add joint basically of the forward operator to this data, what we will get as the reconstruction here on the left-hand side is something that has lost its diagnostic value. So if you give this to a radiologist, it will be likely of no value to him. I mean, you can see probably that bones are intact, but other than that, that's more or less the extent of the value of this image here. And in this talk, I will be talking about some ways to leverage data. So, basically like clean MRI images that exist in data sets or that might be available somehow through internal resources, and how we can use this data to make it such that we can reconstruct an image that retains the diagnostic information, so for downstream applications, while minimizing scan times, and in particular, how we can also make sure that, the reconstruction that we get is a reasonable one. Now, I will quickly talk about the formalization of this problem, since I will be referring to these objects later on, so I want to make sure that it's clear what I'm referring to. Throughout this talk, we will adopt this probabilistic interpretation of the reconstruction problem. So what does this effectively mean? It means that we assume that the underlying anatomy or the images that we want to reconstruct, they follow some distribution. So for instance, here on the upper left-hand side, there is this P capital X, which is the distribution of human knee MRI, let's say. So the unknown signal is an instantiation of a random variable capital X. And in addition, or basically as a consequence, the measurement Y is also a random variable, which is modeled by applying the forward operator that I call A to the unknown signal, and then some noise in addition to this. And what follows from this immediately is actually that the likelihood, so if you have an image, what is the likelihood of a particular datum is actually known. So this we know by how we have set up this problem right here. And assuming that n is just Gaussian noise, then the likelihood can just be written down like this. And in addition to this, I assume that the likelihood is subject to change. So for instance, if I use a different MRI machine, the underlying anatomy doesn't change. It's still the same human knee, but maybe the MRI machine has different scan parameters or uses a different undersampling mask or acquisition sequence. And effectively to reconstruct anything, so from some datum Y, getting an image X, the way we will do it is we are interested in this object on the lower right-hand side, which is just what they call the posterior. So given a datum Y, what does the distribution of reconstructions look like? And in particular, what we want to do is we want to leverage this prior here on the upper left-hand side. So we have access to this prior, maybe a data set of images, and now how can we use this to, get access to this posterior and therefore reconstruct images? And in this framework, effectively, there are two competing approaches. So the first approach, what people did for the longest time in like data-driven approaches, is this discriminative approach. So what does this mean? It means that if you are given a datum Y, what you effectively do is you directly learn the posterior. So for any datum, you just have some model or some model which is either modeling directly the posterior, given this datum y, or which is actually the case more often, just a point estimator. So for instance, the minimum mean squared error of the posterior given this datum y. But here we see actually that this direct learning of the posterior, if you recall the last slide, is kind of weird, because there we are not making direct use of the knowledge that we have of the likelihood, at least not very explicitly. On the other hand, there's the generative approach, which is what I will be focusing on in this talk mostly, where actually you learn not the posterior, but you just learn the prior. So you fit some kind of model to the prior, and then you obtain the posterior through Bayes' theorem. So you explicitly make use of this knowledge that you have of this likelihood, right? Which is right here, the first term in Bayes' theorem. And you augment this likelihood basically by the learned prior. Now, maybe to make the discriminative approach more concrete, or in particular, the learning of a point estimator in the discriminative approach more concrete, what people did for the longest time is you sample some reference signal from your data set, you apply the forward operator, and you add some noise, and this gives you some y. You use some sort of parameterized pseudo-inverse right here to obtain a reconstruction. So this could be, for instance, just a feed-forward network. And then what you do is you just compute the expectation over this joint density right here, and sampling from this joint density is easily realized through this ancestral sampling. So you just sample your signal, and then you apply your forward operator yourself, add noise. This gives you a sample from the joint density. Then you apply some loss function between these two images. So typically this is just the PSNR, for instance, or some similar metric. And then this gives you a gradient with respect to the parameters, and then you tune the parameters of this parameterized pseudo-inverse such that the reconstruction matches the reference signal. And here on the right-hand side, there are just some methods that basically follow this paradigm enumerated. So this includes pre and post-processing approaches. Just for instance, pre-processing approaches would mean that you take the case space, you map it to some fully sampled case space just by some network, and then you have the standard reconstruction pipeline following this. Post-processing would be an instance where you just do a naive reconstruction, for instance, the one we have seen before, just applying the transpose of the forward operator to the data, and then learning the map from this naive reconstruction to the reference data. But there are others, for instance, automap, where there is absolutely no physics used anymore. It's just a direct map from the data to an image. And now I want to basically make one pitfall of this discriminative approach very explicit. And I will do it on this slide by the following experiment. I have here on the upper right-hand side the data. So the data is indexed by some k, and this k is the number of k-space lines that is available to me. And this is also plotted here on the x-axis if you want. So we start at 8% of k-space lines that are available. So this is this auto-calibration region right there. And I will just increase the number of k-space lines that are available to me, right? And on the bottom, I have 3 reconstruction methods. And on the very right-hand side, the image labeled X is the reference signal. The leftmost reconstruction method with the black surrounding is just a naive reconstruction. So we apply the transpose of the forward operator to the data. The red reconstruction method is a post-processing type discriminative approach. So it's just applying a learned unit to the naive reconstruction. And then there's this generative approach where we, modeled the distribution of these knee images and then use them in a Bayesian framework to reconstruct. And I will show you how we actually did that in a few slides. But first, I want to start this experiment. So when I start to press the play button now, basically, it will start to increase the number of k-space lines. The reconstructions will adapt. And you will see here that in the plot, you will see the PSNR of the respective methods to the ground truth. Now, as I start this, you see that as the number of case baselines increases from 8% to 25%, the naive reconstruction basically doesn't change. So adding these high frequency case baselines doesn't really give you anything, at least not in terms of PSNR. The discriminative method starts out very low, as does the generative method. But at some point, this generative method overtakes the discriminative method. And I'm stopping here this video at 25% because this corresponds actually to the setting on which this unit was trained on. So this is an important detail. But you can see that actually already at this stage, the generative approach, so the one that we proposed, and I will go into detail a bit later, is already beating the discriminative approach. And now as I continue this video, something interesting happens. Namely, the red line actually starts to decline. So the performance of the discriminative method becomes worse as more data becomes available. And it's somehow clear that any reasonable reconstruction method should give you a better reconstruction as you have more data, right? Whereas for the generative method, okay, we have some weird stuff going on when there is very little data available. However, after some point, the curve is basically almost strictly monotonic, increasing. And of course, the naive reconstruction basically approaches the reference signal as you get infinitely many data, or all the data, I should say. And I think I stopped here at 99% such that, the PSNR doesn't go to infinity. And here is a very similar experiment, just to drive home the point even more explicitly. What we did here is we just flipped the acquisition around, right? So we rotated the acquisition mask by 90 degrees. And I can just continue to play this video. What happens here is actually that the discriminative method is never better than the naive reconstruction, whereas the generative method always beats the naive reconstruction. And interestingly, it is actually the case that this acquisition mask is beneficial for this anatomy that we have right here due to the alignment of the knee, but that's a detail. So the take-home message here is that the discriminative approach is not a reasonable one, at least not this particular one, because it gives us, worse reconstruction as the number of data increases. So in the rest of this talk, I will focus on this generative approach, and in particular, what are the challenges in this generative approach? Well, first of all, the challenge is actually, how can we find the right model? So how can we go from this distribution P capital X, which is basically just a bunch of images that are on the hard drive, right? How can we go from this to a model, a mathematical model of this distribution that we can then use in downstream reconstruction tasks? The next challenge, of course, is that of sampling algorithms for the high-dimensional posteriors that arise in these problems. So the posteriors that we will look at, they are actually in the order of 100,000 to whatever this is, like 8 with 9 zeros appended to it. So 100,000 is approximately the number of variables that we have in this talk. It's 320 by 320, so images of 320 squared. But it goes up to this number that starts with the 8, for instance, if you consider 3D problems where you have 2K variables in each dimension, right? So how can we efficiently sample from these posteriors? And we want to do all of this while remaining interpretable. So I want to address this first problem of modeling. So what we can do actually is, maybe the naive approach to this modeling problem is the following. We just take some feed-forward convolutional neural network, which maps any image to a scalar that I denote with this R. And then we just say, okay, this corresponds to the negative log likelihood of an image, right? And this is what we did in this paper here, stable deep MRI reconstruction using generative priors. So again, we just map an image to a scalar through a CNN that has this particular architecture right here, and interpret this value basically as a negative log likelihood. And how can we then train this thing? Here on this last bullet point, it's written a bit abstractly. We're just trying to minimize some divergence. For instance, here the Kullback-Leibler divergence between the model distribution and the reference distribution. In practice, of course, this argmin problem right here is the problem of finding the parameters of this map R. So finding the correct convolution kernels and whatever other parameters you might have. But I will not go into detail of this training procedure. I will just talk about once we have trained this model, what can we do with it? And the first thing we can do with it is we can actually sample from the model. So just like you can sample from a one-dimensional Gaussian, you can sample from this high-dimensional probability density if you want. And how we did it is we just started from uniform noise. So each pixel is between 0 and 1 distributed randomly. And then we run this unadjusted Langevin algorithm on this learned model. And what's the deal with this unadjusted Langevin algorithm? Well, if you just implement it like this, then the stationary distribution is actually the distribution that you're interested in. So you're really just sampling from the model if you want. And I will just play these videos again. So we're starting from uniform noise, and quite quickly you will see that actually there appears something which is very reasonably considered anatomy of a human knee. So we can really generate images that look kind of like the reference distribution. And how this helps us is actually, do I have this here? Yeah. How this helps us is that, you know, if we do this unconditional sampling, we can even plot. So as we do here on the right-hand side, we can even plot like the density function if you want. So the golden curve right here is just the Langevin trajectory, and we plot the density function that is given by this learned model. And how this helps us effectively with respect to interpretability is that we can just look at the images that the model is generating and say, okay, it likes, you know, structures that appear in human knees, right? It doesn't, for instance, like faces. It doesn't generate a face. So in any reconstruction problem, it will most likely not impart a face on the reconstruction. Or what we see in addition is that, you know, it likes this type of structure where there's, I guess, the femur and the tibia. So the femur is on top, I think, and the tibia on the bottom. And to the left and to the right of these bones, there's like this fat tissue, and here there's a bit of muscle tissue appearing. So it just, you know, likes this type of stuff. But this was unconditional sampling. So how can we now use the same model for conditional sampling, basically for the resolution of the inverse problem? Well, it's very easy. Instead of plugging into the unadjusted Langevin algorithm the prior, we just plug in the posterior. So now we can just sample the posterior with the unadjusted Langevin algorithm. And on the next slide, I will show these two quantities here, this E and V, that correspond effectively to the mean of the Langevin trajectory as well as the marginal variance. And as previously, this object right here, the gradient of the log posterior, is something very tangible. It's just the gradient of the data term plus the gradient of the regularizer if you want, and then there's a minus sign in front of both of them. And here there is an example of this conditional sampling for a random acquisition mask with acceleration free. And I don't want to go into any detail here regarding the reconstruction, the MMSE reconstruction here on the left-hand side or the variance on the right-hand side. But what I want to do is I want to go to the next 3 slides. And the only thing that will change is this acquisition mask right here, and obviously the corresponding reconstructions. And the acceleration factor that I denote here by R will increase from 3 to 4 to 5 to 6. So this is the only thing that changes as I switch between these slides right here. And effectively, the amount of detail in the analysis that I want to go into right here is the following. As the acceleration factor increases, which means that we have less data available, the variance, the pixel-wise marginal variance also increases. So it effectively means that, you know, we're less certain in the reconstruction if you want. Now, this marginal variance is a nice thing to look at, but what does it really mean? It's not so clear. You know, does it correspond, for instance, to the fact that there is like some unseen structure in the data, right? So for instance, if there is no tumor present in the training data, will there be high marginal posterior variance when there is a tumor in the anatomy? It's a bit unclear, and we tried to answer this by this experiment right here, which is kind of a fun experiment. What we did is we just overlaid the cameraman image into a CT of a human thorax, and then did what we did previously. And what we see actually in the variance plot here on the right-hand side is that there is some high variance regions appearing in regions where the reconstruction kind of looks unnatural, right? So for instance, here on this edge of the cameraman, especially on the lower left-hand side one, it's a very sharp corner, right? Which typically doesn't appear in the anatomy of a human. And on the reconstruction or on the marginal posterior variance, we have this high variance region. And similarly, there's the feet of the tripod of the cameraman that exhibit high posterior variance in the reconstruction. Again, it's hard to interpret this type of stuff. It's just an additional information that we can hand, you know, to the experts that make downstream decisions. But what you can actually do, for instance, is you can use these variance maps to come up with some sort of pixel-wise error bounds, actually using the tools of conformal prediction. And this is what my colleagues did back in Graz in this paper, posterior variance-based error quantification for inverse problems in imaging. So there they have an estimator that somehow depends on the variance that you get, for instance, by this method right here. And then they can say, okay, with 99% confidence, this pixel really is in this interval. Now, I will just quickly go over the reconstruction algorithm that we also proposed in this context for parallel MRI. So in parallel MRI, typically you have this setup where the anatomy X, as well as the capital C coil sensitivity maps, the spatial coil sensitivities of the MRI machine, are unknown. And effectively, there are two approaches to the reconstruction of this of these unknowns. The first one is the offline estimation, or the two-stage estimation, as I called it here, which is where you effectively estimate these coil sensitivities in an offline step, for instance, from an auto-calibration region in the data. However, this is prone to misalignment artifacts, for instance, if there's patient movement. And it makes the acquisition sequence less flexible, because typically it has to be Cartesian, it has to have an auto-calibration region of a certain size and stuff like that. Whereas the joint reconstruction, so basically recovering X and or the S in an inverse problem, doesn't suffer from this. However, the corresponding inverse problem is then a nonlinear one. But for this problem, we have proposed some reconstruction algorithm that you can look up in the paper if you're interested in it. It's basically something like, I mean, it's the IPARM algorithm, if anyone knows it. It's basically two-block vista with a Gauss-Seidel update rule. And, you know, using this first-order accelerated algorithm, the reconstruction problem converges in approximately 50 iterations, which takes approximately 3 seconds on consumer-grade hardware. And here on the lower right-hand side, there's the iteration rule, but it's skipped because it's not so important. Now, what we gain, or what we get with respect to performance now in this parallel MRI problem is the following. So if we compare to this discriminative feed-forward method, the variational network, which is like state of the art, I mean, it's really hard to beat on the thing that it was trained on, we get kind of a similar performance. So, you know, the 1 dB less, but here it's already quite good. So 1 dB maybe doesn't matter so much. However, what matters is if we change the subsampling mask here on the left-hand side, so again, just rotating it by 90 degrees, the discriminative variational network completely breaks down, whereas ours retains its performance basically completely. And in addition to this, and what I'm not showing here with qualitative results, is the fact that we are also estimating these sensitivity maps. And actually, our estimation is typically superior to these two-stage approaches, especially when there is little auto-calibration data available. Now, in the previous slides or in the previous method, we made heavy use of this sampling algorithm. So we used the unadjusted North-Schneier algorithm for training, which I didn't show, and for inference, so for this unconditional sampling and for the conditional sampling. However, there is actually very little theory regarding the unadjusted North-Schneier algorithm for potentials that are non-smooth, which was the case for my network, and non-convex, which also was the case for my network. And so, my colleague, Andreas Habring, and a few other colleagues, we looked at this problem and said, can we actually improve this? So can we improve the situation of these sampling algorithms of high-dimensional posteriors that are non-smooth and non-convex? And we came up with this, well, we didn't come up with this idea of using the Moreau envelope, but we used this idea of using the Moreau envelope, which is a tool from convex optimization, to basically convexify the potential and make it more well-behaved. So basically, what you can see here on this plot below is when you use a high Moreau parameter, whatever this means, you see that these dark red curves are very well behaved. Actually, this the most dark one, if you want, is actually just a quadratic function. And as the Moreau parameter decreases, the potential becomes more and more faithful to the original one. And as it approaches zero, it actually is identical to the original one. And this leads us to this algorithm that we proposed, the diffusion at absolute zero algorithm, which is basically just running the unadjusted North-Schneier algorithm, but not on the original potential, but on its Moreau envelope. And in particular, also, we decrease the Moreau parameter through the iterations, which means that we start at a very easy problem. So for instance, think of the quadratic. And the problem becomes more and more hard and non-convex and non-smooth as the Moreau parameter decreases. And finally, we approach the original problem as the Moreau parameter approaches zero. And what we can do with this then is we can do the same thing that we did previously with the unadjusted North-Schneier algorithm, just that now we actually have the theory to back up that what we're doing is sound. So we converge to the stationary distribution, and the stationary distribution is the one we're interested in. And what I want to point out here on this slide is just on the first row, there's the MY Euler algorithm, which is basically the unadjusted North-Schneier algorithm ran on the Moreau envelope of the problem, but without this annealing. And on the second row, there's our algorithm where the Moreau parameter is annealed from some high value to a very low value. And due to this annealing, we have faster convergence, which is exemplified by this gray arrow right here that points out some subsampling artifact, this backfolding artifact, which is present here for MY Euler still after 600 iterations, whereas it's no longer present for diffusion at absolute zero after 600 iterations. And in addition to this, we have actually the theoretical convergence guarantees. Now, I want to quickly talk about diffusion models as well. These days, you cannot have a talk about these generative models without mentioning the diffusion models. And what's the idea behind diffusion models? Effectively, they do the following. They don't say we want to model the reference distribution, but they want to model the distribution of a random variable, which is actually indexed by a continuous index, if you want. And it's defined by this diffusion stochastic differential equation right here. And then what you do is you can fit some parameterized model to the gradient of the log density of this random variable indexed at time t. Now, it's not so obvious that this is an easy thing that you can do in this setup, but you have to take my word for it that it's possible. But what's the problem with these types of approaches is that actually this conditioning right here, so this gradient of the log density at time t. What the people typically do is they just take some network, which is typically a UNet, and they condition it somewhere, with this t, but no one actually knows what's going on. And in particular, the conditioning doesn't have any relationship to the stochastic differential equation. So for instance, if you swap out the SDE for a different one, you will still use the same network. So there's this relationship missing. And in addition, this function is typically not a gradient where it says it actually models a gradient. So we wanted to have a look at the following question. Can we come up with an SDE and the corresponding model such that if we change this time index, the model follows the stochastic differential equation? And effectively, what we came up with was the following model. So we looked at the SDEs and what we can basically do. And the simplest choice was to just choose F0 and G, a scalar, basically. And under this choice, actually, there's this identity that the density of xt is given by the convolution of the density of x0 with a Gaussian with a particular covariance. And this thing we can actually implement in a model. So for a particular t, it just means that if we can somehow convert the model with a Gaussian, it just means that we have to, well, this is what we have to do. And in addition, if px0 is a Gaussian, it just means that we have to adapt the variance of this Gaussian in accordance to the diffusion time. And then the model that we came up with is basically this type of product of experts model, if you want, with Gaussian mixture model activations. And why Gaussian mixture model activations? Well, first of all, because we want px0 to be a Gaussian. So this is basically the best thing we can do. But in addition, the Gaussian mixture model activations are actually not so bad in some sense. So you can approximate almost any function you want, at least on an interval, if you have sufficiently many Gaussians. And this is what I'm showing here on the right-hand side. So for instance, in the first row, I'm approximating the absolute value potential function, which is a very popular one, right? For instance, in TV regularization or also wavelets and stuff like that, by a Gaussian mixture. Now, of course, this is only valid on an interval, but if you know that your activations are going to lie in this interval, then it doesn't really matter. In the second row, I'm approximating a student T potential by a GMM. And in the third row, I'm just showing that these GMMs can also represent much more complicated functions, for instance, multimodal densities and stuff like that. Now, just to drive home this point, if you're more familiar with this type of writing, so where you write down the negative log prior, basically the regularizer, as people call it, it's just this very familiar structure where you apply some linear operator to the input. So for instance, a convolution bank or wavelets or whatever. Then there is this activation function applied to it. In this case, since we have a Gaussian mixture model density, the corresponding activation function is the negative log sum x. It's a log sum x function, basically. And with this, we can represent all these families here on the right-hand side. So when you train this model, what do you get? You get the filters and you get the activation functions. So I want to excuse these filters right here. Unfortunately, the PDF viewer in Mac does interpolation here for some reason. But these are just, I think, 11 by 11 filters. And this one is, white, black, black, whites, for instance, right? So these are the filters that you get, and these are the corresponding activation function. And the different colors that you see in the activation plots, they correspond to different time indices, if you want. The brighter ones, or for the lack of a better word, brighter ones are where the time index is near 0. And the darker ones is where the time index approaches some finite but large value. And you see that as the time index grows, we have this effect of smoothing these functions, right? Which corresponds to the fact that we really fulfill this SDE, which is the same as a convolution with a Gaussian. And I also have here an illustration of this thing on my website right here. I hope I managed to show this. So what I have here is just this image of the tiger. And for a particular sigma, I'm showing on top the filters. Below the filters, I am showing the thresholding functions if you want, and below the thresholding functions are the potentials. And as I am changing this sigma right here, if it loads, you can see that the image becomes more noisy as there's more noise clearly. And the thresholding functions also change in accordance to the variance that I have selected here. I hope I don't have to go back, yes. And we applied this thing to MRI reconstruction, and I mean, the results are not spectacular. They are better than TV, but I mean, not much better actually, but this is what you can expect from a model, which is kind of like TV in some sense. Now, throughout this whole thing, we have assumed that we have access to this data distribution, right? But typically, it's actually not so easy to get hold of this. So for instance, you don't have access to millions of knee MRIs. You don't have access to millions of knee MRIs of a particular vendor, for instance, vendor of the MRI machine, you know, anatomical alignment, or even different anatomy, for instance, the brain. So what can you actually do when there's no data? Well, the thing is, researchers have shown that diffusion models and these posterior sampling algorithms actually generalize remarkably well. And we wanted to understand why this is the case. And when I looked at this problem, I remembered that Mumford, this Fields medalist guy, back in the day looked at the distribution of gradients of natural images, right? So what is the distribution of two neighboring pixels in natural images? And he showed that actually, no matter which scene you take and stuff like that, they all kind of look the same, actually, which is what I'm showing here on the right-hand side. So most of the pixels are almost the same, which corresponds to this peak here at 0. And then you have this leptokurtic shape, so heavy tail distribution of pixel chunks, if you want. And this led us basically to hypothesize that these out-of-distribution reconstructions are more or less just driven by these local features. And we set out to test this hypothesis by a very simple experiment. We just took the networks that people typically use in these diffusion approaches, and we successively stripped away layers, basically making the model more shallow, reducing its receptive field, and therefore making it more local, if you want. And what are the takeaways of this experiment? Well, first of all, I want to point out this effect of the model size. Okay, so we just look at more or less one type of network, but we strip away layers, which is what's happening as this D is decreasing here. So for each of the plots, from left to right, the model gets more shallow, less deep, right? And again, the level of detail in this analysis I want to go into is the following. If you take smaller models, so for instance, on the upper left-hand side one, as you go from left to right, there's actually no decrease in performance. So this is the first takeaway. If you use smaller models, there is like a negligible in-distribution performance drop. However, if we look at out-of-distribution cases, so here in-distribution versus out-of-distribution means a different contrast. Basically, it's the same anatomy, but a different contrast. So here it's fat suppressed. You can see that actually as we go from left to right, the line is pointing upwards, or most of the lines are pointing upwards. So it means that in out-of-distribution reconstructions, smaller models are better. And now I want to point out this effect of the size of the training data. So these are the two effects that we consider right here. And to test this, what we did is the following. We just trained the same networks, but we trained them on CELEB A, right? And now for this in-distribution reconstruction, which is the in-distribution reconstruction of the knee MRI. So here we're still reconstructing knees, right? However, we're doing it with the model we just trained on the faces of celebrities. The takeaway here is that actually there is almost no difference in performance. So here we're plotting the difference in performance to the previous experiment, and everything is around zero. There is a slight drop here in the in-distribution case. However, in the out-of-distribution case, all of the lines are above zero. So there's a positive jump, which means that the models that were trained on the faces of celebrities are actually better at reconstructing out-of-distribution knees than the model which was trained on knee MRI. And I have a illustration of this as well right here. So what's happening here is on this slider right there, what I'm doing is I'm just changing the trade-off parameter between the data likelihood and the prior, right? And on the left, it's unconditional sampling. And as I go to the right, the data is considered stronger and stronger if you want. And as you can see, when there's zero data, obviously it generates celebrities' faces. And as there is more and more data, it starts to become kind of like a knee. And then there's this threshold right here where there's actually no faces visible anymore. And if I use the full power of the data likelihood, if you want, then it's actually a very reasonable reconstruction. I mean, it's almost a perfect reconstruction. Okay, so what if there's no data? Well, the scarcity of the data can be mitigated at least to some degree. So there's a bit of an in-distribution performance drop and stuff like that. But to some degree, it can be mitigated through the adaptation of the model capacity. So making the model smaller or adapting it to the task at hand. And through the training on abundantly available natural images. So for instance, if you want on the faces of celebrities, but maybe just on some natural image data set of natural scenes. And what you can do in addition is just fine tune on this data set that you have. Okay, so in conclusion, what we have is we have these days expressive models that lead to exceptional reconstructions. And we have some ways to make these reconstructions as well as the models interpretable through posterior sampling or through principled modeling. What we still require is these sampling algorithms for the high-dimensional posteriors. We still require some understanding of the architecture. So for instance, people just use these noise conditional score networks for the diffusion models, right? But it's completely unclear what's going on, at least with the conditioning and stuff like that. And what we need in addition, which would be a really interesting research direction, in my opinion, is this type of feedback loop. And what I mean by this is all of these reconstructions or these methods that we have looked at in this talk, they basically stop at the data, right? We don't go further back than the data. But why don't we go to the scanner, for instance, and adapt scan parameters such that, for instance, we minimize the marginal posterior variance, or that we minimize some error with respect to the posterior or something like this, right? Why don't we go back to operators? I mean, the guy who is operating the MRI machine, is this reconstruction good or not? I mean, here we're just using these PSNR and SSIM metrics, which are actually completely useless to some degree. So this would be a very interesting research direction, in my opinion. And with this, I want to thank you for your attention and as well the online audience. Thank you.